G on the track, boy.
Assalamualaikum and hello everyone. My name is Atsin. Today I will present the introduction of this experiment. This experiment is about coefficient factor, or we can known as friction factor. The main aim of this experiment was to determine the pipe friction factor and head loss, and to show how the friction factor varies with Reynolds numbers by manipulating the flow rate of the fluid in the pipe. In this experiment, pipe friction factor, pressure loss or head loss for a flow subject to friction will determine experimentally, and the flow is considered steady at Reynolds number where Re bigger than 2320. With the turbulent pipe flow, the pressure loss is proportional to the length of the pipe. Second, coefficient of pipe friction. Third, density of the flowing medium. And fourth, square of the flow speed. Next, for the objective of this experiment are to determine how the flow rate, pipe diameter and surface roughness affect the friction factor of a flowing fluid in the pipe. Next, to discuss the factor that affect pipe selection based on significant head loss. And lastly, to determine the factor that affect the inaccuracy of the data.
Hello, my name is Ahmad Zikri and I will present to you the theory for this experiment. So in general, in turbulent flow, between 2 points for horizontal, which is Z1 is equals to Z2, the pipe which has constant internal diameter with no minor head loss are accounted, whereby the total head loss is equals to major head loss. The pressure loss and major head loss can be determined by using Bernoulli equation as follows. So for the first equation, the P, which is pressure loss between 2 points, is equals to FL, which is the coefficient of pipe friction, is dimensionless, and L is the length of the pipe in meter. FL is over 2D, D is the internal diameter, and times rho V square. Rho is the density of the water, and V is the speed of the water. So for the second equation, HL is equals HL, which is the total head loss, major head loss, is equals to FL over D times V square over 2G. FL same as the previous equation. D is also the internal diameter, V square also, and 2G is the gravity constant. For the turbulent pipe flow, the coefficient pipe friction is depends on the equivalent pipe roughness and the Reynolds number. The table, as you can see here, is to show the examples of the equivalent roughness based on types of pipes. So for example, we have riveted steel pipe, concrete pipe, wood stiff pipe, cast iron pipe, and so on. So as you can see here, the figure 2 shows the Moody chart to summarize the relationship between Reynolds number, coefficient pipe friction, the pipe roughness, and the internal diameter. So before to find the Reynolds number, we can use this formula, which is the Reynolds number is equals to the speed of the flowing medium times the internal diameter of the pipe over divide by the kinematic viscosity of the flowing medium. So from the previous equation, we use to find the Reynolds number, we use the kinematic viscosity of the flowing medium. So in this table, the table shows the kinematic viscosity of water. So the viscosity varies based on the different temperatures. So as you can see here, the higher the temperature, the lower the viscosity of the water. So for the speed of flowing medium can be calculated by using this equation, which is V is equals to 4Q over pi D square. So V is the speed of flowing medium, and Q is the flow rate of the flowing medium, and D is the internal diameter of the pipe. Okay, so for the turbulent flow in smooth pipes, the F which we using the Blasius formula is valid if the Reynolds number is before 100,000. So this equation is F equals to 0.316 over 4 root of Reynolds number. Okay, so to find the coefficient of pipe friction, we can also use the Colebrook formula, which is the equation, which is this equation, the 1 over f square root of f is equals to negative 2 log in brackets the roughness of pipe over diameter and over 3.7 plus 2.51 over Reynolds number times the square root of f. So for this equation, it must be iteratively resolved. So first, we estimate the value of f, placed it at the formula, at the Colebrook formula. So we calculate the initial approximation. This approximation is reused in the equation to calculate a second approximation. So if the estimated value is taken from the Moody chart, the initial approximation is generally sufficiently accurate, and the values only differ after the third decimal place. So the F in turbulence flow could be determined by using a Moody formula, which is F is equals to 0.001375 cube root of 1 plus 200 times roughness of pipe divided by internal diameter, and plus 10,000 divided by Reynolds number. So alternatively, the values of F can be directly obtained by using a Moody chart. That's all from me. Thank you.
Hello everyone, I am Chua and I will continue the presentation with the topic of apparatus and metrology. First of all, we are going to use fitting hose, gate valve, technometer, rotameter, 2-tube manometer, 6-tube manometer, differentiation, pressure sensor, digital display for pressure, pump switch, main switch, electronic pressure sensor, return hose, return valve, water tank, drum valve, and pump based on the arrangement in the left side picture. Next, we have to prepare the experiment pipe as our measuring section. The first one is galvanized steel pipe with the internal diameter of 12.7 mm, copper pipe with the outer diameter of 18 mm and thickness of 1 mm, PVC 20 with the outer diameter of 20 mm and the thickness of 1.5 mm, PVC 16 with the outer diameter of 16 mm and thickness of 1.8 mm, PVC 22 with the outer diameter of 22 mm and the thickness of 1.9 mm. The following is about the methodology part. First of all, both the feeding and return hose connected to a galvanized steel pipe. Tube were used to connect the inlet H1 and outlet H2 of pipe with manometer. Main switch is turned on and pump is activated. The gate valve is opened slowly until the reading of rotameter reaches 2.0 meter cube per hour. Brake ventilation valve is opened until all the bubble release. Brake ventilation valve is closed after that. Right ventilation valve is opened slowly until the preset minimum reading of 2-tube manometer reaches 35 mm. The gate valve is opened slowly until H1 reaches maximum and H2 reaches minimum value. The gap valve is adjusted to reduce the flow rates for next reading until the water level in rotameter reach minimum value. The height, temperature, and flow rate value for each reading is recorded. Next, the reading for differential pressure was taken at a digital display screen 1 by transferring the manometer tube to the differential pressure sensor box. Both experiment is labeled. The red ventilation valve at the differential pressure sensor is opened to release the air bubble. The red ventilation valve is closed and the value of flow rate, temperature, differential pressure reading are recorded. State C until state 10 is repeated to adjust the flow and record the new data. Lastly, all manometer is removed from the system, the gap valve is closed and the pump is turned off. Step 1 until step 12 is repeated by replacing galvanized steel pipe with copper pipe, PVC 16 pipe, PVC 20 pipe, PVC 32 pipe with the preset minimum reading of 2 tube manometer of 1 mm, 35 mm, 30 mm, 22 mm. This is all my presentation. I will pass to my friend now.
So the next part is the result of this experiment. For table 3, this is the data for galvanized steel pipe, which have internal diameter of 12.7 mm and length of pipe of 1000 mm. Then, from this experiment, we can get the value of H1 and H2. From this value, we can calculate the value of delta H by using formula H1 minus H2 divided by 1000. This is because the value of delta H is in meter. Then, for table 4, this is the data for copper pipe that have 18 mm diameter pipe, 1 mm thickness, and 1000 mm of length of pipe. We calculate the same thing like table 3, but for table 4, we also calculate the internal diameter of this pipe. The next one is for table 5. Table 5, we get the data for PVC pipe that have 30 mm outer diameter, 1.5 mm thickness, and 1000 mm length of pipe. Then, we also get the value of H1 and H2 and calculate the delta H. The internal diameter that we get for PVC pipe is 17 mm. The outer diameter, which is 20 mm minus by 3 mm, and we will get the internal diameter. Then, for table 6, this is the data for PVC pipe that have 16 mm outer diameter, 1.8 mm thickness, and the same length, which is 1000 mm. We calculate the same thing like the other table. And for the last one, this is the data. This is the data, which is data for PVC pipe that have 32 mm outer diameter and 1.9 mm thickness. We get the value of H1 and H2 by doing the experiment. And also, we calculate the delta H. We also calculate the internal diameter. So the last one is we calculate the velocity average for each table, the Reynolds number, and the equivalent roughness by using the formula given. From this data, we can do the discussion for this experiment.
Hi, I'm Aida. I'm going to present the discussion for this experiment. So the first question is, compare the coefficient of friction F for each of the test pipe in your experiment with the coefficient of friction F from Moody chart and calculation using a formula of Glacius, Coolbrook, and Moody. Explain on the possible reasons for the difference in their values. So as we know, we have several formulas to calculate the coefficient of friction, which are Glacius formula, Coolbrook formula, and also the Moody formula. So all these three formulas are different, and if we use Glacius formula, F is equal to 0.316 over quad root of RE. If we use Coolbrook formula, 1 over square root F is equal to -2 log, open bracket, relative roughness over internal diameter, over 3.7 plus 2.51 over RE times square root F, close bracket. And if we use Moody formula, F is equal to 0.001375, open bracket, 1 plus 200 relative roughness over internal diameter plus 10 to the power of 6 over RE, close bracket, and to the power of 1 over 3. So our group has calculated the coefficient of friction using those different formulas. And before we calculate the coefficient of friction, we need to determine the type of flow first, whether it is laminar or turbulent, or whether it involves both, which means that they have a transition between those type of flows. So from the calculation, the coefficient of friction for each of the test pipe using Beche's formula, Moody chart, and Coolbrook formula are similar to each other, except for the coefficient of friction calculated for galvanized steel pipe using Beche's formula. However, these values are slightly different when we calculate the coefficient of friction using Moody formula. Why? This is because Moody formula provides an accuracy of plus minus 5% for smooth pipes and plus minus 10% for rough pipes. So we rank the pipe based on their major head loss. The pipe with the biggest diameter has the lowest head loss compared to the other pipes. This is because it has relatively lower velocity and friction factor, as well as big internal diameter. So as we know, the formula for major head loss is HL equal to coefficient of friction F times length times velocity squared over 2 times internal diameter G. So although length is one of the parameters used in calculating head loss, it doesn't influence the differences in total head loss of the pipes in this experiment, because all the pipes that we use have the same length, which is 1 meter. So the only factors that influence the head loss are friction factor, velocity, and also the diameter. So based on the formula of head loss, the total head loss is proportional to friction factor and velocity, but it is inversely proportional to diameter. Question number 3 is about the factors contributing to errors or inaccuracy in experimental data and the possible recommendations to improve the existing results. So the first error could be the parallax error. Parallax error could occur due to the incorrect position of the observer's eyes to the reading scale. So we could fix this error by ensuring that the position of the eye is perpendicular to the reading scale of the apparatus. Number 2, they might have air bubbles trapped in the system although the ventilation valve was open. So we need to open the ventilation valve several times until there have no air bubbles in the system. And lastly, water level in the manometers cannot be calibrated and fluctuates heavily. So we need to adjust the volumetric flow until it doesn't fluctuate, or we could take a few readings, and lastly we take the average reading.
Lastly, for the conclusion, after completing the experiment, the objective to determine how the flow rate, pipe diameter, and surface roughness affect the friction factor of flowing fluid in a pipe is obtained. Then, the factor that affect pipe selection based on significant head loss are the pipe diameter and flow rate, because the bigger the pipe diameter, the lowest velocity and friction factor, then it makes the lower head loss. Lastly, there are some errors such as systematic error and random error while doing this experiment. To avoid this error, we can do the precaution that been represented by IDA. That's all from us. Thank you.